So you can stop in between. You can ask questions, any kinds of questions. You can stop in between. You can ask. So it will be highly interactive. No, don't hesitate to ask any questions. So the course, as you already know, it's on the computational electromagnetics. So I will not discuss about the syllabus and reference book, which is already available in the website. I hope you can hear me. The sound is coming properly.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So this website is the course web page. Now here I will put all the lectures and the link to the YouTube website. So you can go there, then you'll find the lectures, slides, then even the video recording which we are doing for the class. And so mark distribution, I think many of you have already attended the last course. No, last semester only I think 2 students are new here. So we'll have an in-class evaluation. So that means how active you are in the class. No, how much is your participation in the class? So active. Last time we gave it 10 marks. So this time we are giving it just 5 marks. And this is a computational electromagnetic course. So usually, let's say you consider this kind of courses abroad, then they usually don't have this examinations like mid-semester exam and semester exam. They usually have a project. They usually have a programming exercise. But here we cannot do everything with just exercise, programming exercise. So we'll give programming exercise 35 marks. So that means you will have assignments which are given 1 week before. You'll submit it after 1 week. So in the class, I will give you some assignments which are related to computational electromagnetics. You have to write some small MATLAB codes, and there will be around 7-8 of them. So it will carry 35 marks. So this is a major major portion of evaluation for this course, computational electromagnetics. So then you will also have some online evaluation. So online evaluation is usually during the class, you'll be asked to solve some problems or something like that. Just like your mid-sem or end-sem, we'll have 3 of them. So each of them will carry 20 marks. So this will be along the similar lines we have done in the last semester. And the only difference now is we have a programming exercise which carries huge tentative mark distribution for the course. Syllabus I'm not discussing is because we'll learn only 3 techniques here. I will briefly discuss it after in today's class itself. And the reference books are many. I have listed many of them. So you can visit the website after the class and find out. For different portions, we have a different book. So let's go to the next slide. Just before starting with the computational electromagnetics course, let us try to look at the presently available commercial softwares. We have many softwares, and who is working in the RF and photonics, or let's say other related areas, and most of the time you use a commercial software to do your simulation works. Nowadays, without commercial softwares, you cannot do your research. So it's a bare necessity nowadays. So in the electromagnetics area also, we use many softwares, commercial softwares, and we do the simulation. Then after that, we do experimental results. So let us look at some of the softwares which are available commercially. Some of them is, one is EMSS software. Probably people call it as FEKO also. This is a very popular software. So this software, so basically what I want to show you is that all the softwares, commercial softwares, are actually originated from the university research, research which has been done by students during their PhD program or MTech program under the guidance of some professors, and it finally led to the origination of many commercial softwares. Like EMS software is FEKO. If you just type FEKO, then you'll be able to get this software. And this is one of the antenna used for designing antennas, passive devices, filters, and what actually this software is originated by this person here, Dr. Jacobus. He is actually a student of see, when you look at the references, one of the major reference we'll be giving for this course is Computational Electromagnetics book by Professor Davidson. Professor D.B. Davidson, he's a professor at University of Stellenbosch in South Africa. So this Dr. Ulrich Jacobus is basically a PhD student of, actually he's not a PhD student, but the Frank Mayer is a PhD student of D.B. Davidson. So these two persons actually originated this software, which is called EMSS software, and it's one of the most widely used and antenna and passive device design software in the RF and photonics community. So what this is one software which has been your own company. Let's say you are very good in programming and you like the area computational electromagnetics, you can actually start your own company, and you can market your own software. So this is actually one area which is always green. No, I always tell my students, one area in the computational electromagnetics is which is always green. That's because if you look at the electromagnetics field theory, it's a very old subject. So it's already saturated. You cannot do anything new there. Everything is well defined. But if you go to computational electromagnetics, this is a always evergreen subject. So this always keeps on, growing. It is it's not saturated. So every year you'll have some techniques for science also. The programs you'll be writing would be on different algorithms in the computational electromagnetics, and with the advancement of computer science, this area is always growing. So there is no saturation here. And if you want to start your own company, or if you are very good in programming, you can always start your own company. And okay, so let's go to this is one example. Another example is IE3D. This was a very common, widely used antenna design software in the recent past. So when I first started my antenna design, I used this IE3D software. But nowadays we have another better software, which is called a high frequency structure simulator. So this IE3D software was the software which was widely used software, and you can also observe that this is started by a PhD student, and his name is Jian Zheng, and he did PhD under Professor D.C. Cheng. So he's the president emeritus of New York University. So what you observe is most of the commercial softwares which you are using is actually originated in the academic research in the universities. I3D is one of them, EMSS is one of them. Then even you also have XFTDD. This is a FTDD based software, and we'll learn FTDD in this class. Also, what is FTDD? So XFTDD is a software based on FTDD started by MoM. This is also actually originated in Pennsylvania State University by some Dr. Raymond Levers and Dr. Christopher Penny, and with this fellow. So what you observe is most of the software which are available in the market which are widely used are actually originated from academic research. So this is a golden chance for you if you are really interested in starting your own company and you write your own codes and you want to uh, sell some commercial softwares. Then you can always do. Another example is Sonnet. Sonnet is also widely used commercial software. You can always search in the internet. This is actually started by Dr. James Rossio. He's actually a PhD student of Professor R.F. Harrington. So R.F. Harrington is actually the originator of method of moments. So we'll also learn method of moments in this course, FTDD method of moments, and we'll also learn finite element method. So now this Sonnet software is also started by James Rossio, who is a PhD student of R.F. Harrington. R.F. Harrington is a professor in Syracuse University. He is the originator of method of moments in the electromagnetics. Method of moments also exist in other areas like mechanical engineering, mathematics. But actually, for application for EM area, R.F. Harrington is the person who originated this method of moments. Then we also have GEMS software is actually started by Dr. Wenhua Yu. Actually, he was actually a visiting professor. When I went to Penn State University, I actually had some interaction with Professor Ras Mitra. He has a very large group, And Professor Wen Yu was a visiting professor at that time. So that time he didn't start this software. So later on I find out that GEMS software is actually started by this Dr. Yu. He was a visiting professor at Professor Rasmitter's group at Penn State University. So you can keep on finding. So basically all the softwares, commercial softwares, has always contribution from the academic research. So and yeah, so this question, no? Can you guess the price of software like high frequency structure simulator? Any idea? You must be using high frequency structure simulator. You know what is high frequency structure simulator? Anyone use this? See, you can
Yes, sir.
always, yeah, so you have used it, right? So can you guess the price of this high frequency structure? We also have it in our lab, in our department of EEE, we have high frequency structure simulator. We prepared it few years back, around 7, 8 years back. And can you guess the price? One software, how much is the price for software like high frequency structure simulator? No idea?
It is in
Yes, sir.
lakh.
1 lakh per month.
Okay, so we have a perpetual license. We have perpetual license means we can use forever. And when we actually try to buy this software around 10 years back, it is almost 7 to 10 years back, that time the cost was around 1 crore. So, but then we are lucky because we are educational institute, they give us 80%, 85% discount. So we got it in 15 lakhs or something like that at that time. So it must have been increased a lot by now. So you can understand what is the price of this kind of commercial software. And anyway, all the softwares are developed in the research lab in the academic institution, either by PhD student or by some researcher who are working in this area. So and if you are very much interested in starting your own companies, write your own code, sell some commercial software, this is one area which you can always explore. So by the way, what is this computational electromagnetics? Why do we need this computational electromagnetics? So if you have any questions, you can stop and ask me in between. So don't worry about the recording. So let it be there. It would be a live class. So what is this computational electromagnetics? So basically, you have learned in your electromagnetic field theories, and it has been claimed by your instructor that once you know 4 Maxwell equations along with the boundary conditions, you can explain all electromagnetic phenomena in nature. But then, why do we need this computational electromagnetics? So everything can be solved with Maxwell equations, but that's not true. Let's say you have some practical solutions which doesn't have analytical solutions, not tractable solutions. You don't have exact analytical solutions. Many of the problems are like that. Many of the practical problems doesn't have, closed form solutions. So those kind of solutions we try to solve numerically using numerical methods. So in the computational electromagnetics, we'll try to solve real world practical problems which cannot be have any kind of analytical solution, closed form solutions. So we'll use numerical methods to solve the approximate solutions, and it's highly accurate. You'll take some examples. We'll see some examples. This computational electromagnetics, even if it is an approximate method, it is highly accurate. And so that's the idea. Basically, we want to solve practical, complex electromagnetic problems which doesn't have analytical solutions using numerical methods. That's what we're going to do in the computational electromagnetics. So why do we need this computational electromagnetics? Why not directly fabricate and test our device directly, without doing any kind of simulation? That's not actually advisable, So why we need this computational electromagnetics? Because see, before we fabricate and test our device, okay, just before that, there's some difference between the science and engineering. Science basically, you come up with usually an equation or theory, then it ends up there. But as an engineer, what we do is we want to use those equations. Our research start, our work start from that equation. We try to use that equation, and we want to design a device, optimize its performance. So there's a lot of optimization going on for the engineering field. So in the engineering field, as an engineer, you should be able to optimize the performance of the device, not just the equation. So equation is actually come up by most of the physicists or science people, but they end up there. But we start from there, use it for designing some device, try to improve its performance. So ours is not just one way design. You just use a formula and finish the design. Those kind of design is not possible. So we need to have optimization. We need to So now if you have a commercial software, if you write your own code on the system, on the computer, you can design, you can simulate it, you can keep on doing all those simulations many times on your system before you do the fabrication. So let's say if you fabricate your antenna or your filter, once you fabricate it, that's the end of the story. After that, you cannot change the device. So, and anyway, fabrication also sometimes is very costly, very difficult to do it. But if you have a software, if you optimize the performance of your device using the software, using computational electromagnetics, then you can just fabricate the best device. So you have to do all those hard work before you fabricate your device. But if you keep on just fabricating your device without doing the simulation study, you whatever results you are getting in this commercial software, after you fabricate and test it, they actually closely match. So you don't need to worry about the accuracy of the software. Most of the softwares are very accurate, like high frequency structures simulator. Whatever you do design using the software, if you do proper simulation, after you fabricate and test your antenna or any device, you'll get similar kind of performance. So you have to use the softwares which are actually developed using computational electronics for finding the best performance of the device before you fabricate and test it, before you do the experimentations. So this is a precursor to the experiments. You have to do all this hard work before you do the experiment so that you don't waste resources. So experiments, fabrication, you have to use a lot of resources. You cannot do it 100 times, 1,000 times, but simulation, you can do as many as you want until unless you get the best performance. Another thing is that some of the experiments are very difficult to, perform. Like, for example, you consider, light testing many of their regular equipments. So those kind of experiments you cannot do it experimentally because it will spoil the equipment. So instead of that, you can do simulation. You can always do simulation by developing a software which is based on the computational electromagnetics. And as I already told you, it's not possible to conduct some of the experiments because of limited resources and facilities. So this is the motivation behind the, why we are using computational electromagnetics. Okay, so let's say as a student, how do you learn this computational electromagnetics? This is a course which you cannot just learn by reading it, understanding it. You have to implement it. So that's why I have given you a huge weightage on your programming exercise. Until unless you do it, you write your own program. You start with a very simple program, then gain confidence, go for a more difficult program. So like that, you have to learn computational electromagnetics. Cannot be just learning by heart. You look at the course, you study it, you learn it by heart, and that's the end of the story. That's the starting. Basically, what is more important is your implementation of the codes. So computational electromagnetics, I usually say it is learned by doing it. You cannot just read it and understand it. You have to do it. So for that, you have to do programming. So programming, usually you can take any programming language. I have no restriction on that, but usually we use MATLAB because it's convenient for many of the students also. So usually we'll use MATLAB programming language, and I think most of you must have already used MATLAB programming language in your previous classes. And if you don't know, you can always explore it, and it's quite easy. So in this class or in this course, we'll be concentrating on three methods, computational electromagnetic methods. One is matter of moments, another is finite element method, another is finite difference time domain method. So these are the three most popular uh, methods which are available in the computational electromagnetics. There are many more methods. It keeps on said that I have already told you at the beginning. So this is an ever-growing field, so it never saturates. So every year, there will be a new techniques coming up, new algorithms coming up. So and the proof for that is that look at the books which are written for the electromagnetic field theory. You'll not find good books in the last 5 to 10 years. So because that field is already saturated and somebody who has written a very good book on that field will be still used by students for many years. But now you look at the computational electromagnetics, there will be always one few books which are coming up every year. So this is a ever growing field. It's a green field, you say it. So it never saturates. So this is one area where you can always expect something new is coming. Okay. If no questions, then we'll start with the method of moments. The method of moments is one of the most popular methods for analysis of antennas. So basically, method of moments is very useful for designing antennas, optimizing the performance of antennas. You can develop your own code to do simulation for antennas. That is because method of moments is a 2D. So basically, you have a 3D antenna structure also, but method of moments would actually do the analysis of the, let's say you have any antenna, most of the antennas are usually made up of metals. No? But when I apply method of moments, I will just consider the patch portion, only the metal portion, which is on the above the substrate. So usually the analysis we do in the method of moments is over the source region where you have a current density or magnetic current density. So that portion is very small. So we do just discretization of the structure only over the source region where you have a source current, magnetic current density or electric current density. Then you can find the fields everywhere in infinite space. So this is a very efficient technique. It's very fast. But if you consider finite element method or finite difference time domain method, is a 3D based method. So method of moments is a 2D based method. Even if you have a 3D structure, we'll just concentrate on the source portion and try to find the fields everywhere. But if you consider finite element method or finite difference time domain method, you have to consider the whole region 3D structures. So that's a major advantage and it's very efficient. But here, developing a program is not so easy as you compare to the finite difference time domain method. Later on, you'll see that finite difference time domain method is basically discretization of the Maxwell equations in over space and time. So if you want to learn finite difference time domain method, you just need 1 week. So you want to write your first program in finite difference time domain method, you just need 1 week. But let's say if you then you have to spend a lot of time, maybe at least 1 month, 2 months, 1 semester. That is because there is some difficulty involved here. But then once you write your code, this is going to be very fast because this is 2D based simulation method, but other methods are 3D based methods. So this is very efficient, very fast, very efficient. Antenna usually keep it in free space. So for those kind of structures, method of moments is a very good technique. So we'll start with this. And here we'll actually start with the simple example of electrostatic problems. So like how to find a charge. So basically electrostatic problem. We don't have any electrodynamic fields. Everything is very simple. So we'll start with the simplest one, then go for the more difficult cases. So in the same procedure also we'll start with 1D structure, 2D structure and so on. So we'll start with electrostatics, then we'll go for electrodynamic fields. Once you know the steps or method of moments for the electrostatics problem, you can extend it for electrodynamic fields, which are very complex. So in this, apply the technique for a simple problem in electrostatics, then you can apply it for electrodynamic fields. So just before that, we can even apply this MoM for differential equation. Everybody knows how to solve a very simple differential equation. We'll try to solve a differential equation applying the basic steps of MoM, and we'll see that the solution we are getting from actual solution by solving the differential equation and by applying approximation using MoM is almost matching. So those kind of things we'll first do it. We start with the simple problem, first understand the steps of MoM, then solve very simple problems, then go for the complicated problems. Okay, so what's there next? So let us try to see what is this MoM, method of moments. So basically MoM, I would start with an example so that you don't get confused. So look at this equation here. You have integral equation for line charge density. Lambda is the line charge density. This is a potential. No? See, basically this is the electrostatic problem where I want to find the potential due to a line charge. You must have come across this in your electromagnetic field theory. So once I have the line charge density, I can always find the potential by integrating it. No? This is a line charge. If there's a line charge density, you multiply with the length, you get the charge. No? So let's say I want to find potential B is equal to Q by 4 pi epsilon 0 R. No? That's same formula, but here I am having a line charge density. So lambda x is the line charge density. So once I have this line charge density, how is the behavior of this line charge density? Then I can always integrate and find the electric potential. So that's a usual problem, but in the matter of moments, see, you look at the practical way of looking at this equation. So how can you know the line charge density on the line? On a, let's say you have a metal rod. How do you know the line charge density of the B naught on metal wire? You want to find the line charge density. So the problem is inverse problem. It's not, you don't know the line charge density, but in your undergraduate courses, you assume the line charge density is known, then you find the potential. But this is a reverse process. We actually don't know the line charge density, and we know the potential. We know the potential we have applied. So the potential is given to you. So I want to find the line charge density. So can I use Maxwell equation or any kind of equations you have from your fundamental electromagnetic field theory and find out this line charge density? You cannot do it. This is because you don't know what is the line charge density. See? So here we can apply this technique, method of moments, to find this line charge density. So just before that, let us define what is the integral equation. So here the unknown lambda is the line charge density is under an integral sign. So usually you have differential equation, but here we call this as integral equation. That is because unknown is under the integral sign. So unknown U is lambda. Voltage you are applying is known to you. And this whole thing here I can represent it by L operator. So I'll call it this is L operator, integral operator. This integral operator is defined as dx dash by 4 pi epsilon 0 r x comma x dash. X is the observation point, x dash is the source point. So what is the source? Source is the charge. What we are observing is the potential. So depending on your source and observation point, you'll have different value of x and x dash. So This kind of equation where your unknown is under integral sign, we call it as integral equation. You must have heard of differential equation, but integral equation, if you have not learned MoM, then you don't know. So this kind of equation is called integral equation, and you already know what is differential equation. So now MoM is a technique. No? Actually, MoM is a technique which will solve this kind of problem. This kind of problem. This is an integral equation problem. You can also have differential equation problem, and you can even have combination of those two. So MoM is the technique which will actually solve the integral differential equation. That means it can have integral equation also, it can have differential equation, or have also it can have only one of them also, both of them also. So MoM is a method of moments technique which actually try to solve these integral differential equations using the numerical methods. So in that, what it basically does is actually try to convert this integral differential equation to a metric system of linear equations. So linear equations like ax is equal to b, x is a noun. So this kind of equation will convert it into a linear equation like ax is equal to b, x is the noun, a is noun, and b is noun. So you can find out what is the x unknown. So the idea is basically you try to convert this integral differential equation to a linear equation. So we'll discuss that. So the idea for the method of moments is convert the integral differential equation to a metric system of linear equations, and you can use linear algebra to find the solution. So what we are trying to solve is of the form LU is equal to K. L is a linear operator. It could be integral differential operator. We have already seen one integral operator here. This one example. Like that, you can also have differential operator, del by del, del x, del square by del x square, those kind of operators. So L is an operator which will have both integral and differential operators. This inhomogeneous integral differential equation into a metric system of equations. Okay, let's take examples. For example, this differential equation you have here. This is a commonly used differential equation. You have dou square fx by minus dou square fx by dou x square is equal to 3 plus 2x. So what is the noun here? Is the function fx. And what is known? 3 plus 2x square. This is known. What is the operator? Minus d square by dx square. So different integral differential equation. This is a differential equation. The previous one is a integral equation using the method of moments. So what is the first step? Approximate the unknown function u. So unknown function u in this case was lambda x. Lambda x was unknown function u. In this case, unknown function u is f of x. This kind of unknown functions, we actually approximate it by sum of weighted noun basis function. It's a linear approximation. You have unknown function u, you actually do linear approximation of that summation n going from 1 to infinity. If you do it 1 to infinity, you get absolutely accurate results, but you cannot do that. Infinite means when you write your code, you cannot have any infinity. You have to have a very last number. You cannot have infinity. So a noun function is actually approximated by n going from 1 to n un. So where basically un is in bn. In is a noun constant, bn is the basis function. We call it expansion function, also basis function. These are actually noun functions. These are noun functions. You actually approximate the noun function in terms of noun basis function by this linear approximation, where you actually approximate the periodic functions by sine and cosine function, similar to that. So here, this basis function, there is standard basis function for MoM. So what you are doing is you are actually approximating the noun basis function by noun basis function. So this is the linear approximation. In, see, basically in the MoM, what we need to find out is this in here. We actually approximate the noun function by in bn. N is going from 1 to capital N. So if I know this, then I know the approximation of this unknown function. That is the solution. So the whole process is to find out this in here. So I cannot see the time. So if I'm running out of time, you can just tell me, because I'm sharing the screen. So anyway, from next class onwards, I'll put a watch here. So this function of a periodic functions. So here basis function are cosine and sine functions. This is very clear. You have already come across this in your undergraduate studies. So now, what was our equation? Our equation was LU is equal to K. But U, I have approximated it by summation n going from 1 to capital N, and Bn. In that case, this will no longer be approximation, no longer be equal to, it will be approximated, because our U is actually approximated by this expression here. So when I put instead of U here, the equation LU is equal to K will no longer be equal to here, it will be approximation. So the error we are getting from this approximation, you can always find out. So the error is called residual error. Residual error is basically K minus this. Matter of moments usually in the mathematics. No, so we have computational electromagnetics in mathematics department also, and even in mechanical civil also. They actually their orientation is little bit different. So this residue here, we actually try to minimize it to 0. So mathematicians usually call this as method of weighted residuals. So it has something to do with this residue here. We actually weight it with some function and try to force it to 0. So that's why it's called method of weighted residuals. So mathematicians, if you go to mathematics department and take this same computational electromagnetics course, they will not say method of moments. They call it method of weighted residuals. Weighted residuals, we'll see it. So the first step, what was the first step? We approximate the unknown function by non-basis function using a linear approximation. What is the next step? Next step is we actually enforce the boundary condition. We actually make the inner product of the above equation with the testing or weighting functions and force it to 0. Make the residue equal to 0. So next step is that testing. We call it testing. So we actually do the inner product of the above equation. This equation here, we do inner product with another function which is called testing function. But in matter of moments, usually we take this basis function and testing function equal many times, and that's one of the popular techniques. So your basis function and testing functions are equal, and there are standard functions for that. Okay. So next thing is we do the inner product with the weighting functions and force it to 0. So that's the process you have here. So we denote the inner product as this sign here. This sign here is for the inner product. We do inner product with the testing function and force it to 0. And we do it over different values of m. M is going from 1 to capital M. Usually we take this m equal to n. So in that case, this will also go from 1 to capital N. In that case, our matrix will become square matrix. And anyway, in is a constant. We can take it outside and we can simplify the previous equation. We have first term, second term here. You transfer the second term to the right hand side, keep the first term to the left hand side. Then what you have is summation n going from 1 to capital N, Wm inner product with linear operator operating on the basis function equal to inner product of weighting functions with the noun functions. Is it clear? So now n is going from 1 to capital N. M is also going from 1 to capital M. If I consider m is also going from 1 to capital N, this will give you a matrix. Let's see that. But just before that, what is this scalar product? So the order doesn't matter because this is a scalar. So you do integration of multiplication of function g and w, integrate over interval. This is called scalar product. So these properties will satisfy for the scalar product. BF plus CG, you do scalar product with W, you can simply take out B common, then do the scalar product of f and w plus c comma that was the idea. No, what was the method of moments? Method of moments actually convert the integral differential equation into a metric system of equations. And this metric system of equation is zi is equal to b. I was unknown. Z is we can calculate it. B also we can calculate it. What is this I? I will have I1, I2 up to I capital N. This is the unknown questions. We want to find it from the method of moments. Once you have that, you can actually find a unknown function as I and B and summation n going from 1 to capital N. B is a non, this B you can calculate because this is basically scalar product of non-function with the testing function 1, 2, 3 and so on. So this is a vector. And this is a Z matrix. Z matrix is W1 scalar product with the linear operator operating on the basis function B1. So you can calculate all of this. Then you can find out this I matrix, I vector. Then you can find out what is the unknown function. Okay, I think I should stop here. Stop recording. Why is that?